Okay, let's dive right into this explainer and decode the architectural blueprint of chemical bonding. आज हम इस complex class 11 CBSE topic को बिल्कुल simple बनाएंगे. We're going to mix Hindi and English to make this chemistry topic super easy and honestly incredibly visual. If you've ever looked at a chemical formula and wondered how that thing actually exists in the real world, well, you're in the exact right place. Grab your notes, focus on the concepts, and get ready to literally visualize these molecules in popping 3D. Let's start building.
सो सबसे पहला और सबसे इंपॉर्टेंट सवाल, एटम्स अकेले क्यों नहीं रह सकते? आई मीन, व्हाई डू दे कॉम्प्रोमाइज देयर इंडिपेंडेंस टू फॉर्म बॉन्ड्स? वेल, दे बॉन्ड टू अचीव स्टेबिलिटी, जस्ट लाइक अस, राइट? इन द यूनिवर्स एवरीथिंग वांट्स टू बी इन द लोएस्ट पॉसिबल एनर्जी स्टेट. अकेले रहने में एनर्जी ज्यादा होती है, रिएक्टिविटी ज्यादा होती है. इट्स chaotic. But when atoms come together and form bonds, they release that pent-up energy. They achieve this nice, stable, relaxed state. Think of the noble gases. They're basically the cool kids of the periodic table. They are already perfectly stable, so they really don't react much. Every other atom out there is just trying its hardest to be like that. ये रहा हमारा syllabus checklist for today's explainer. We'll cover the foundations of chemical bonding, covalent versus ionic bonds, bond parameters and energy, 3D geometry via VSEPR, and finally, overlapping, resonance, and polarity. Let's jump right in.
Starting off with Section 1, Foundations of Chemical Bonding. Let's see exactly how our atomic bricks are laid out.
Now, what's really fascinating here is the core principle governing almost everything in basic chemistry. सबसे पहले आता है the famous octet rule. This principle tells us that every single atom is constantly striving to get exactly 8 electrons in its outermost shell for ultimate peace and stability. 8 electrons matlab noble gas configuration, right? Whether they have to lose electrons like sodium, gain them like chlorine, or share them like carbon, उनका ultimate goal बस एक ही है, somehow reach that magical number 8. Now obviously, as you'll see in your advanced CBSE exams, there are a few interesting exceptions like incomplete or expanded octets, but this definitely remains our foundational rule.
Exam point of view से ये particular steps absolutely crucial हैं. This is exactly how you draw Lewis-Strauss structures without messing them up. Step 1, gather up all your valence electrons. Step 2, lay out the atoms. Always put the least electronegative atom right in the center. Step 3, start distributing those electron pairs around to satisfy that octet rule we just talked about. And finally, Step 4, calculate the formal charge. Formal charge हमें mathematically बताता है कि molecule का सबसे stable version actually कौन सा है. For instance, when you draw the ozone molecule, O3 in your class 11 exams, calculating that formal charge is exactly what proves which oxygen gets the double bond and which one gets the single bond. It's basically a math check for stability.
Moving smoothly to Section 2, Covalent versus Ionic Bonds. अब देखते हैं the two main ways these atoms actually interact to reach that stability.
So, ये स्लाइड हमारी केमिकल बॉन्डिंग की दो अलग-अलग दुनिया दिखाती है. एक तरफ हमारे पास आयनिक बॉन्ड्स हैं, जहां इलेक्ट्रॉन्स का बिल्कुल कंप्लीट ट्रांसफर होता है. एक एटम अपना इलेक्ट्रॉन दे देता है और दूसरा पूरी तरह उसे ले लेता है. Just like in sodium chloride or table salt, the result? Massively strong electrostatic forces between those newly formed positive and negative ions. और दूसरी तरफ we have covalent bonds, जहां atoms एक दूसरे के साथ electrons थोड़ा gracefully share करते हैं. Neither atom wants to give up an electron completely, so they just compromise. Think of methane, CH4, or water, H2O.
But wait, because nature isn't always perfectly black and white. This is where things get super fascinating. Fajan's rule is a guaranteed concept in your exams, so let's really break it down. It shows us that the strict line between ionic and covalent is actually super blurry. Believe it or not, even a pure ionic bond has some hidden covalent character. अगर cation बहुत छोटा और highly charged है, like lithium for example, तो उसकी polarizing power बहुत ज़्यादा होती है. वो बगल वाले anion के electron cloud को अपनी तरफ literally खींचता है, उसे distort करता है. और ये जो electron cloud की slight sharing या distortion होती है ना, यही actually covalent character लाती है ionic compounds में. Mind blowing, right?
Alright, Section 3, Bond Parameters and Energy. Let's measure our architectural blueprint, because the forces holding these atoms together aren't just abstract ideas. They have very real technical parameters.
And this table brilliantly illustrates the relationship between bond order, length, and energy. Just look at the trend here. Bond order is simply the number of bonds between two atoms, single, double, or triple. जैसे जैसे bond order बढ़ता है, say you go from a single carbon-carbon bond to a triple bond, the physical bond length छोटी होती जाती है. atoms और पास आ जाते हैं. They get pulled tighter together. But correspondingly, the enthalpy, which is the energy needed to break that bond, drastically increases. एक अकेली लकड़ी तोड़ना आसान है, पर 3 लकड़ियों का बंडल तोड़ना मुश्किल होता है, right? That is exactly how atomic bonds work in the real world.
Now for the really fun part. Section 4, 3D geometry via VSEPR. Paper and 2D drawings से बाहर निकालने का वक्त आ गया है. Let's see how all this builds into 3 dimensions.
I want you to imagine a 3D animation right now, right in front of you. Picture a central atom with electron pairs dynamically rotating to push each other as far away as possible. Since all electrons have a negative charge, they literally hate each other. 2 bonds make a perfectly linear 180-degree shape, like in beryllium chloride, BeCl2. 3 bonds make a flat, triangle-like trigonal planar shape, like BF3. 4 bonds pop out of the screen into a 3D tetrahedral pyramid, like methane. And in CBSE Class 11, you'll even see 5 pairs form crazy trigonal bipyramidal shapes like PCl5. The actual physical geometry of the universe is shaped by electrons just trying to avoid each other.
Finally, bringing it all together in Section 5, overlapping, resonance, and polarity. This is where classical chemistry meets quantum mechanics. जब हम slightly higher level पर जाते हैं, we realize electrons aren't just solid little dots. They actually exist in blurry clouds called orbitals. You know, S, P, D, F. जब atomic orbitals 3D space में एक दूसरे पर overlap करते हैं, तब actual physically strong bonds बनती हैं. Head-on overlap gives you a super strong sigma bond, while a sideways overlap gives you a pi bond. And then there is resonance. कभी-कभी एक single drawing molecule की पूरी reality explain नहीं कर सकती. Concepts like resonance help distribute that electron cloud evenly across the whole molecule, giving it massive extra stability. Ozone again is an absolutely perfect example of this electron delocalization.
So the crucial takeaway here is that understanding a molecule's 3D shape and its bonds directly leads us to dipole moments. अगर electron sharing unequal है, तो molecule के एक तरफ partial negative charge आता है और दूसरी तरफ partial positive. This creates a dipole. But because molecules exist in 3D, we have to add these dipoles up mathematically, just like vectors. Carbon dioxide में 2 dipoles एकदम opposite direction में होते हैं, so they just cancel out to 0, making it entirely non-polar. But water is bent. The dipoles don't cancel. These dipole moments aren't just theoretical numbers on a chalkboard. They dictate the actual physical and chemical properties of the substances around us. It's literally why water dissolves salt, but oil doesn't.
तो हमेशा याद रखिए, everything we discussed today is beautifully connected. What starts as a simple Lewis dot structure on paper, just basic dots and lines, actually expands into complex 3D orbital overlapping that dictates the very reality of our 3D universe. Every single substance around you is shaped by these exact architectural rules. So, armed with VSEPR and an understanding of dipoles, I want to leave you with one final, provocative thought. Knowing that electron lone pairs repel even harder than standard bonding pairs, want to guess what exact, life-giving shape water takes in 3 dimensions, and why that highly specific, weird little angle makes all life on Earth possible? Think about it, and we will definitely explore that next time. Keep learning.